Hi guys, it's Mrs. Bird. Welcome to today's lesson on scientific notation. Make sure that you have a packet in front of you before we get started. So again, today's lesson is on scientific notation. We're going to apply some of these things we've been learning about the laws of exponents to working with scientific notation. So let's go ahead and get started. Okay, the first slide you have in your notes, and by the way, I need you to make sure that you are recording these notes. Your classwork grade today will be based off of the notes that you take. So make sure that you're following along with the video and taking notes appropriately. Again, your note taking will be your grade for the day. So let's start by completing this table, this powers of tens table. I'm going to start you off, but I think you probably can fill this out yourself. Let's start with 10 to the 0 power. Any number to the 0 power would give us 1. So let's go ahead and put a 1 there. All right, what about 10 to the first power? 10, good. And 10 squared, that's 10 times 10, 100. And 10 to the third power, 10 times 10 times 10, yep, 1,000. All right, you can keep going. If you notice here, our exponent represents how many zeros we'll have behind our 1. So 10 to the fourth power would be 10,000, where we have 4 zeros behind our 1. All right, you continue filling out the table, at least for this first column, while I do the same here. Okay? So look up when you get a chance and um, check this column with what I have up here to see if you have the same numbers. Now, just for time's sake, we're going to skip this column where we're listing the common name, partly because you don't have enough room on your paper, but I think we can get the idea of this without filling out that column anyway. So let's go ahead and move on to um, when we're raising our base 10 to negative exponents. So whenever we're raising a number to a negative exponent, it becomes a fraction. So 10 to the negative 1 power becomes 1/10. Good. And if I'm writing 1/10 in decimal form, what is 1/10 equivalent to in decimal form? Excellent. 0.1 or 1/10. What about 10 to the negative 2 power? 1 over 100, which in decimal form is equivalent to 0.01. Okay, you continue. 10 to the negative 3 would be 1 over 1,000. Our decimal equivalent is 0.001. Okay, you continue filling out the chart on your own and look up when you're finished. Okay, so continue to fill that out if you have not finished already. I'm going to talk through while you finish that up. Okay, so on the next slide, the question there is, what patterns do you notice in this table? So if you look back, I already mentioned one pattern where when we're raising a number to a positive, when we're raising a number, when we're raising the base 10 to a positive exponent, the exponent tells us how many zeros are behind our 1. But what's happening here when we're raising base 10 to a negative exponent? Okay, jot down what you're noticing here, what patterns you're noticing. Okay, we'll confirm your ideas in a video that we'll watch in just a bit. How can you tell how many zeros are in a number based on the power of 10? Well, kind of the same thing we just talked about. How can you tell how many zeros are behind your decimal and how many zeros are behind your 1 when you're raising to a positive exponent? Jot down those ideas, the answer to those questions, and we'll confirm them in a bit. Okay, so moving on. How wide is our universe? Well, it's this many miles. This number is written in standard notation. When numbers get this large, it's easier to write them in what's called scientific notation. Does anyone remember scientific notation, perhaps from science class or from 6th grade math? I hope so. But we'll talk about what scientific notation is. So scientific notation is basically a way to express a number in the form of A times, always base 10, to some exponent, where A is between the numbers 1 and 10, and N is an integer, meaning it's a positive or negative whole number. So again, this number A will be between 1 and 10, and your exponent will be some integer, a whole number, positive or negative number. All right, so let's go back to the width of the universe. If we want to write this in scientific notation, this big old number here, first we need to figure out, where does our decimal point begin? Where's our decimal point right now? Sure, it's right after this last 0 here. So I'm just going to place my decimal here just so that we can see it. So again, in scientific notation, we're writing it expressed as some number A that's between 1 and 10. So let's go back to our width of the universe. How can I move this decimal so that it makes this number between 1 and 10? Where can I move this decimal to make this number between 1 and 10? Sure, I could move it right here between the 2 and the 1. Don't you agree that 2.1 is between 1 and 10? Sure it is. Again, make sure you're copying these down in your notes. I left some blank spaces there to make sure you fill them in. Just a reminder, you want to take notes so that you can get your classwork grade for the day. Okay, so now how many decimal places did we move the decimal? Remember, we started here at the end and we moved it all the way over here between the 2 and the 1. Count how many decimal places we moved it. Hopefully, you're going to say 23. So again, our goal is to write it in scientific notation. That's A times base 10 to some integer. All right, so when the original number is more than 1, So our original number was that big old number here with our decimal at the end. When that number is more than 1, the exponent is going to be positive. So your answer in scientific notation would be 2.1 times base 10 to the 23rd power, where 23 here represents how many times you moved your decimal. This base will always be 10, and the first number, A, will always be a number between 1 and 10. Okay, it's that number where you moved your decimal to make it between 1 and 10. Okay, let's move on. What if we start with this little bitty number here? Don't you agree that this is a very small number? Sure it is. Where would the decimal go to make this number between 1 and 10? Hopefully you're thinking to yourself, between the 9 and the 0, making this 9.02, or more properly 9 2/100ths. Okay, so how many decimal places did we move our decimal? How many places did we move our decimal to get it between 9 and 0? Let's count. 1, 2, 3, 4, 5, 6, 7, 8 places. Okay, so if we're writing this in scientific notation then, and our original number was less than 1, then our exponent is going to be negative. Again, when you start with a number that's less than 1, like our original number here was 0.0000000902. So if that original number is less than 1, a very small number, then our exponent is going to be negative. So in scientific notation, this should look like 9.02 times 10 to the negative 8 power, where negative 8 represents how many times we moved our decimal to the right, and the 9.02 is our number when we moved our decimal to get a number between 1 and 10. Let's practice one. Let's look at this number. 28,750 and 9/10. Okay, first we need to figure out where our decimal is and how many times do we need to move it to get a number between 1 and 10. Okay, if we place our decimal place here, if we move it to between the 2 and the 8, we get a number that's between 1 and 10. So we moved it 1, 2, 3, 4 places to the left. We know we're going to have we know that 4 will be our exponent, since that's how many times we moved our decimal. That eliminates these two answer choices. All right, remember, if our original number is greater than 1, then our exponent will be positive. So since our original number was 28,750.9, our exponent is going to be positive. Therefore, our answer is this third one here. Let's keep going. Okay, what if we start off in scientific notation and we want to express it in standard notation? Standard just means regular. How do we express it as a regular looking number? Okay, so if our exponent is raised to the negative 4th power, where do you think we're going to move our decimal? Sure, to the left 4 units. So we should end up with the number 0.00018. We've taken this decimal and we're moving it to the left 4 units. 1, 2, 3, 4. You can fill in these empty spaces with zeros. Sorry for writing on top of that, but you get the idea. All right, so if it's raised to a negative 4 power, we know we're going to have a very small number. We're going to end up with a small number when we're writing it in standard notation. I hope you're still taking notes. Okay, what about here? 4.58 times 10 to the 6th power. We have a positive exponent, so we should be thinking that this is going to give us a very big number, which it will. We're moving this decimal 6 spaces, 6 units. So if we do that, 1, 2, 3, 4, 5, 6, I'm going to fill in these empty spaces with zeros. So we should end up with the number 4,580,000. Let's keep going. All right, yes or no? Are these numbers written in scientific notation? Let's look at number 1. 42 and 6/10 times 10 to the 8th power. Is that written in scientific notation? Hopefully you're saying to yourself, no, it's not. Why not? Because this number here is not between 1 and 10. Remember, this number has to be between 1 and 10. All right, so number 2, is this number between 1 and 10? 9600ths? No, this is not written in scientific notation. That number has to be between 1 and 10. All right, let's try number 3. Is 4 and 6/10 between 1 and 10? Sure it is. Yes, this is written in scientific notation. A couple other things to remember. This base number has to be 10. Okay? Try these on your own. Write each number in scientific notation. I'll give you about a minute to do that. Okay, look up. Did you get what I have here? Let's briefly talk about these. Okay, 62,400. You would move your decimal place. Starts here. You're going to move it 4 units to the left to get a number between 1 and 10. That number being 6.24. These zeros can drop off the end. All right, times 10 to the 4th power since we moved our decimal place 4 units. Same thing here, except we're moving our decimal 4 units to the right. We started off with a number below 1, so our exponent is going to be negative. We moved it 4 units, the exponent is -4, and we had to move it between the 8 and the 5 to get a number that's between 1 and 10. Okay, for this last one, our decimal starts here. We're moving it between the 1 and the 6 to make it a number between 1 and 10. That number being 1 and 602, what's that, thousandths. And we moved it 6 decimal places, so that will be our exponent. It's raised to the 6th power. Okay, moving on. Let's go backwards now and practice writing again in standard notation. Here we're starting off in scientific notation. I want you guys to write these in standard notation. I'll give you about a minute to do that. Okay, look up and check your answer with mimes. And number 7, we're moving our decimal 5 units to the left. At number 8, we're moving our decimal 4 units to the right. And on number 9, we're moving our decimal 3 units to the left. Okay, let's skip this very last slide. I just don't want you guys to have to get up and grab a calculator, but I promise we will look at how scientific notation looks like in a calculator later. Do not get up and grab a calculator. Okay, so next you will need a purple pre-algebra textbook. If you don't have one already, they are located in the cubby. While you grab those, I am going to show you a quick video on how scientific notation is used outside of a mathematics classroom. So quietly get a book if you don't have one already while I get this video going.
The human body has fascinated ancient and modern scientists alike. Even though it's one large mass, our body's host to a multitude of microscopic cells. You hop on the doctor's scale to determine your overall body mass. But how do you express the mass of things too tiny to register on that scale? One way is with scientific notation. We can use scientific notation to represent virtually any rational number, and it can help us compare very large or very small things. Scientific notation is a way of writing any number as a number greater or equal to 1 and less than 10, multiplied by a power of 10. So you can use it to express the weight or mass of your whole body in pounds or kilograms, or ounces, tons, milligrams, or micrograms. Or you can use it to express the mass of teeny tiny cells and parts of cells that make up your body. Powers of 10 are used in scientific notation. The exponent on the 10 tells us how many times the base number is used in multiplication. Let's go inside the human body. The average adult has about 5 liters of blood, or roughly 5,000 grams. Meanwhile, a single red blood cell's mass is about this number of grams. We can write these numbers in scientific notation. The exponent of 3 means we multiply 10 times itself 3 times, which is 1,000. But what's the negative exponent? That means it's 1 divided by the base to that power. So 10 to the minus 11th power is 1 divided by 10 to the 11th power. So this is a very low number, close to 0, but not as near as 10 to the negative 20. But 10 to the negative 20th power is even lower, nearer to 0, than 10 to the negative 11th power. DNA is our genetic code. You can think of this molecule as containing our body's blueprint in a way. DNA's vital info determines how our cells function, develop, reproduce, and ultimately determines traits like height and eye color. Despite how fundamental DNA is to our lives, it's so tiny that we need an electron microscope to see it. So how can we describe something as small as DNA's mass in meaningful units? Scientific notation is a useful tool. It can represent low numbers in a condensed form. A number written in scientific notation is expressed as a number greater than or equal to 1 and less than 10, multiplied by a power of 10. Since you can't put DNA on a human-sized scale, we use molecular mass. In standard notation, a molecule of bacterial DNA has a mass of this number of grams. Look how much less than 1 it is. Scientific notation is a simple way to express this very low number. Let's see how. A number raised to the negative power is the inverse of the number raised to the same positive power. This is the basis for the low numbers in scientific notation. So 10 with a negative exponent is the same as 1 divided by 10 to that power. It tells you how many places to the left to put the decimal point. Follow the place value pattern. An exponent of negative 1 is the same as 1/10 equals 0.1. And an exponent of negative 2 gives us 1/100, which is 0.01. We can convert this number into exponent form by moving the decimal point 15 places to the right. For each place we move the decimal point to the right, we have to represent the exponent of 10 as a negative number, one less than for the previous place. So the scientific notation expression is 1 times 10 to the negative 15th grams. See how scientific notation makes it easier to express and read this number than in its standard notation shown with all the zeros? Remember, that's about the mass of one molecule of bacterial DNA.
Okay, great. I hope that some of your conjectures were confirmed. Some of those things that you noticed as we did our beginning chart and thought about the patterns in that chart. Okay, so in front of you, you should have your textbook. Go ahead and open up to page 215 according to your packet. Page 215 should look something like this. Now, for time's sake, we're going to actually skip page 215 and 216 because much of that we went over already in the PowerPoint we just did. So we're going to skip again page 215 and 216. And we're going to start with example number 4 on page 217. Now, as you're doing some practice problems later, if you like to go back and look at examples 1 through 3, you can. It will help you remember how to write these in scientific notation and back to standard notation. But we're going to start at example 4, which is a little different than what we did in the PowerPoint, but still related to scientific notation. All right, so in the space provided in your packet, under the last slide in the PowerPoint, go ahead and write down example 4. And we're going to be looking at the problems under the check understanding. So we're on page 217, looking at example 4A. Example 4A. Write this down on your paper. Okay, so 4A, we're starting off with 16 times 10 to the 5th power. We want to write this in scientific notation. Well, you may say this is already written in scientific notation. It's not. Why not? Well, because our number here is not between 1 and 10. Remember, this number has to be between 1 and 10. So how do we make it between 1 and 10? Well, if our invisible decimal starts here, oops, no, I always do that. Let me write 4A back up here. All right, so again, our decimal is here. We're moving it 1 unit to the left. So in scientific notation, this would be written as 1 6/10 times 10 to the what power? I'm hoping some of you said to the 6th power. Okay, when we're moving this decimal, that means that we're multiplying by another 10. Or 10 to the negative 1 power, if you would like to look at it that way. I'm sorry, 10 to the 1st power. Okay, so that exponent becomes 6. Let's try B. These problems are under the check understanding section. Okay, we start off with 0.203, and we're multiplying that by 10 to the 6th power. Okay, this is not yet in scientific notation until this number is between 1 and 10. So I'm going to move this decimal 1 unit to the right to make it into a number between 1 and 10. When I do that, this becomes 2.03 times 10 to the what power? Sure, to the 5th power in this case. Okay, we're moving the decimal 1 place over to the right, so we're going to take away 1 from our exponent. Let's do C together. Here we're starting off with 7,243 times 10 to the 12th power. In order to make this number between 1 and 10, we would move our decimal place 3 units to the left so that this number becomes 7 and 243 thousandths times 10 to the what power? Okay, we've moved it 3 units to the left. So we're going to add 3 units to 12, bringing that to 10 to the 15th power. Okay. All right, so basically when you're moving your exponent to the left, you're going to add to your original exponent. I'm sorry, when you're moving your decimal to the left, you're going to add to your original exponent. And when you're moving your decimal to the right, like in this case, you're going to subtract from your original exponent. If you'd like to go back and read the example here, you're more than welcome to help you with that a bit more. Okay, again, I hope you're copying these down in your notes. Now we're going to skip over example 5, where we're just ordering these numbers from least to greatest. We'll have some more practice with that later. But let's go ahead and skip example 5 and move to example number 6. And I'm going to erase this, so hopefully you have this copied down already. Okay, example 6 is on the next page, page 218. Okay, so in example 6, we're going to start off with numbers that we're multiplying together. Numbers that are in scientific notation that we're multiplying together. So there's an example here, but we're going to do one of the check understanding problems together. Then I'm going to let you do one on your own. So under the check understanding, example number 6A, we have 4 times 10 to the 4th power times 6 times 10 to the 6th power. Okay, so we're going to start off by using the commutative property of multiplication, which states that we can rearrange these numbers Okay, so sorry, again, we're going to start off with using the commutative property, which states that we can rearrange these numbers in any way and it would still be the same problem. So I'm going to rearrange this to read 4 times 6, just taking these numbers here and putting them together. 4 times 6 times 10 to the 4th power times 10 to the 6th power. Again, all I've done is rearrange these numbers. 4 times 6 times 10 to the 4th power times 10 to the 6th power. Okay, hopefully you're going to start thinking about those laws of exponents. So here we can multiply 4 times 6, which is 24. And here we have two numbers that we're multiplying together that have the same base. What's our multiplication rule when we're multiplying two numbers with the same base? What do we do with their exponents? We add them together. So this becomes 24 times 10 to the 10th power. 24 times 10 to the 10th power. Okay, so our task is to write this in scientific notation. Is this in scientific notation? Well, not yet, because this number has to be between what two numbers? Good, 1 and 0. So to do that, our decimal originally starts here. We're going to move it 1 unit to the left. Okay, once we do that, this becomes 2 and 4/10. times 10 to the what power? 11. Excellent. So just to recap, basically, all we did was rewrote this using the commutative property of multiplication, which states we can write this in any order and it's still the same problem. So I arranged it so that our base 10s are together. Okay, so 4 times 6 would be 24, and then 10 to the 4th power times 10 to the 6th power would give us 10 to the 10th power. Not yet written in scientific notation, so I took my decimal, moved it so that I have a number between 1 and 10, and then I added to my exponent to represent that move of the decimal. Okay, I'm going to give you about a minute or so to do example B. This was example 6A. You're going to do example 6B on your own. Okay, look up. If you haven't finished, go ahead and finish up. But for 6B, you should have, if you've done it correctly, 5.68 times 10 to the negative 3 power. Okay, example number 7 gives you one more problem like this, um, written as a word problem, a real world type problem, but you're more than welcome to go ahead and try that one as well to see if you got the hang of this. Okay, so on number 7, under the check for understanding that's written in your book, it's not written up here, but it's in your book. On number 7, you would be multiplying 1.67 times 10 to the negative 27th power times 6 times 10 to the 3rd power. When you multiply 1.67 times 6, what do you end up with? Okay, and then when you add the exponents here, negative 27 plus 3, what do you end up with? Okay, take that number, move your decimal so that it's between, so that you have a number between 1 and 10, and then take away from your exponent. Okay, so we're going to stop there. If time permits, I would like you to go ahead and complete page 219. Let's do numbers 1 through, let's say, 33, and we'll do odd only. This is in your textbook. So your classwork is page 219, numbers 1 through 33, odd only. That's if time permits. I do want to go ahead and jot down your homework, which will be page 94 in your workbook. So the substitute will tell me how much time you had to complete your classwork. If it's not enough time, that's okay. But I do want you to do your homework in any case. I will post this video lesson on Edmodo for you to go back and look at if you like as you do your homework. Just a reminder that you can log into this textbook. I can put that information, that login information on Edmodo as well, but it is on my website. If you need to go back and look at some examples that will help you do your homework. So again, it's page 94 in the workbook. You're going to do all of those. Page 94 in your workbook, all. Write that down. Page 94 in your workbook, all. Okay, thanks guys. Thanks for listening. I will see you on Monday when I return.